In this video we're going to talk about state space modeling of systems. In class we mentioned that we're going to use transfer functions mostly in this class, but state space is another very valuable way to approach things. Again, state space is more targeting modern control theory where we want multi-input, multi-output systems, but certainly it has relevance to you as well. So let's start with the state. The state is the smallest set of variables such that the knowledge of those variables and knowledge of the input is going to completely determine the behavior of the system, where the behavior of the system is the values of those state variables and also the value of the output. And so that's a little wordy, but I think you're going to see it by examples here. And the set of variables that make up the state are going to be called the state variables, which I think is obvious. But these are not necessarily measurable quantities. For instance, if you choose that you've got a mechanical system and you want your position and velocity to be the states, even though you may only be able to measure position or only measure velocity, you can still use both of them as states. Also, if you were to have that same system and you needed to transform the system, say you were doing some modern control and you needed something that was a little more mathematically tractable, a little easier for the computer to crunch, you might apply a state transformation where the physical significance of both of the states would be lost, but they would still be a state whose value tracked the system and would allow you to determine everything about it. But in that case, it's not a physical measurable quantity anymore, it's just an arbitrary number. But in either case, whether things are all measurable, whether they're physically significant or not, the state variables map out an n-dimensional space, and that's called the state space. And so we put them into a vector. Remember, a vector is a 1D matrix, and so we call that vector the state vector. Now we're going to take our equations of motion, and we're going to write them out as first-order ODEs so that we can line them up nicely with our state vector. And so we'll put them in here where we're going to set them up as first-order ODEs, one derivative, and so each equation will have will define one derivative of one state. And so in this case we had Q1 through Qn, so we're going to have n equations. Q1 dot is equal to such and such, Q2 dot is equal to such and such, and these functions can be different, and they can be functions of all the states and all the inputs. Again, this is a state space where you can have multiple inputs. So we've got all our inputs, we've got all our states, and we've got one derivative of each state. And then we'll take our output equation and we'll do the same sort of thing. And we might have P outputs. It's a multi-input, multi-output modeling method, so we could have a bunch of outputs, and these are all going to be functions of the states and the inputs, and I'll show you some examples of these. But to get to our examples, let me just give you the process. You're going to start by identifying the state variables, and so if you know you've got an nth order ODE, then to put that into first order ODEs, you're going to end up with n first order ODEs, and so you need n state variables. So the simple choice is usually position and velocity if you're using a mechanical system. There are other choices for electrical systems and thermal systems. You can also come up with other options, but these are the natural choices, position and velocity. Other options may end up with a more complicated representation, but it still would be an equivalent representation. So once you've got your state variables, you need to eliminate your algebraic equations, and you need to convert your differential equations into differential equations in terms of the states. And so when you do that, you should end up with relatively simple equations that you can split into first-order ODEs, and you'll see that in the examples. So once you've got your first-order ODEs for your state equations, you write your output equations in the same sort of way. You're going to put them in terms of the state variables and the inputs. And then if you've got a linear system, remember linear means it obeys linear superposition, which is most everything we're going to do in this class, then we'll put it into matrix form. And the matrix form is going to look like this, where you've got an x dot, which is going to be my state vector. I'm using an x here instead of a q. People use them interchangeably. And we've got our u vector, which is all our inputs, and we've got our y vector, which is all our outputs. So here it is to summarize that. We've got U as our vector of inputs, Y as our vector of outputs. A is what we call the state matrix. Notice that it converts from the current state to the derivative of the state. B is our input matrix. It takes the input and converts it to the derivative of the state. C is the output matrix, and D is the feed-through matrix. If you want to put it in terms of a block diagram, using Laplace terms, we can do it like this. And we can convert back and forth between transfer functions and state space. If it's a one-to-one state space, we can go back and forth easily. If it's a multi-input, multi-output system, then we'll have to go to a transfer function matrix, which is just a matrix with each term being a different transfer function. But you can do that sort of conversion, and it's not a one-to-one process. You can have many different state space representations of the same transfer function. But back to the block diagram. So if you look at your block diagram here, we've got our input U on the left, we've got our output Y on the right. And so the feed-through matrix is the one up top, the D matrix. That's the one that takes the input and goes straight through to the output. That's why it's the feed-through. In the middle portion, we've got our input matrix B. We've got that integrator, that's the 1 over S term. If you don't remember your Laplace, we're going to review that soon. So 1 over S is an integrator. And since it's an integrator, we know on one side of the state, one side of the integrator is going to be the derivative of the state, or the state vector, and on the right side is going to be the state vector. And so if we have our state matrix there, then you can see that reading this equation, x dot is equal to ax plus bu, which is our equation from the matrix form. We also have a output matrix, and so our output then y is equal to c times x plus d times u, and again that's our output equation from the matrix form on the previous slide. So let's do a quick example. This is a very simple example, and I know it's a very simple example because it's only got that one capacitor. It's only got one energy storage device here because the resistor is going to dissipate energy. And so I need to know the number of states. Well, there's going to be one derivative, and there's going to be one energy storage element, so that's going to be one state. And in fact, I will choose the state as the voltage across the capacitor. Why choose the voltage across the capacitor? Well, in this case, it works out nicely. You could try something else, and you would probably come back to this one, voltage across the capacitor, as being the easy choice. Now my input, I know that I'm applying an input, the voltage on the left, V sub S, and then the output is sort of nebulous. You kind of have to know what the point of the system here is, and this one's just an example, so it's not a real obvious one. But I'm going to choose the output as going to be the voltage across the resistor. And so if I apply Kirchhoff's voltage law, I can say that the voltage across the source there is going to be the same as the voltage across the resistor plus the voltage across the capacitor. And if I apply Kirchhoff's current law, I can say that the current through the resistor is the same as the current through the capacitor. And I can use Ohm's law on the current through the resistor, except I've done it incorrectly here because instead of V sub R it should be V sub C. But in any case, if we've got that and we know our current through the resistor and through the capacitor, I can do oops, they're out of order. I can also do the current through the capacitor as C times the derivative of the voltage across the capacitor, and that's just from our definition of a capacitor. And so if I take those equations, I can rearrange them, and I can get V sub C dot is equal to negative 1 over RC times VC plus 1 over RC times VS. And so that is a state equation, because again, my state Q is equal to V sub C. And then I can also make an output equation where my output V sub R is going to be negative 1 times VC plus 1 times VS, and that comes from my KVL. So that is a one input, one output state space where I've only got one state. That's a really easy example. Let's look at a slightly more complicated example. In this one, I've got a block that's moving back and forth, and it's got a spring and a damper and an applied force. So if I apply Newton's second law, I can say that the force minus the damping minus the stiffness is going to be equal to mx double dot. Again, the x double dot is my acceleration. And so I usually put the dot terms, all the x terms, I guess would be a better way to put it, on one side. So mx double dot plus bx dot plus kx is equal to f of t. So what do I need to know in order to solve this? I need to know initial conditions. So x of 0 and x dot of 0. So if I take my EOM, you can see that it's got 2 dots, so it must have 2 states. So what do I choose as my states? The easy choice is position and velocity. Q1 is position, Q2 is velocity. And so Q1 dot is x dot, which is the velocity, which is equal to Q2. And Q2 dot is equal to x double dot. And I'm going to choose my output y equals x, and that's just based on assuming that I only care about the position of the block, and there's really not a lot else in this example to look at. And so I can write out my state equation. So x double dot is negative b over m x dot minus k over m x plus 1 over m f of t. That's just rearranging algebraically. And so now if I take that, I can substitute and make it q2 dot is equal to negative b over 2 q2 minus k over m q1 plus 1 over m f of t. And I can make a matrix out of that. So q1 and q2 dot, I've got my matrix with a 0, 1, negative k over m, and negative b over m. And the 0, 1 portion of the 0, 1 row there comes from the fact that I chose position and velocity, one of which is a derivative of the other. And I've only got my f applying to the second equation there. So there's a 0 in the first part. And then I can write out my output equation. Again, my output is just y equals x, and in this case that's y equals q1 plus 0 q2 plus 0 f of t. So there I go. I've got 2 states. I've got 1 input, 1 output. But that's a slightly more difficult example. And as a final example, let's consider a 2 degree of freedom suspension system. So in this case, the suspension system in your car, we can break it up into quarters. And so if I take a quarter of the car and call that M1, and then it's got a spring and a damper representing the suspension system, which of course is going to be much more complicated in actuality, but this is a simplified model. And Q2 could be the mass of the tire moving up and down, where K2 is then the stiffness of the compressed air and the rubber of the wheel. So x sub r is the input from the road, x sub 2 is the motion of the wheel, and x sub 1 is going to be the motion of the car, which would be, assuming it's a rigid body, then that's also the motion of the driver. So I've got 2 EOMs here. I've written them out for you. They both have 2 derivatives, so we've got 4 derivatives total. So how many states do we need? We need 4 states. 4 derivatives, 4 states. So let's choose x1, x1 dot, x2, x2 dot. Excuse me. So if I take derivatives each of those, you can see that again q1 dot is equal to q2 and q3 dot is equal to q4. And I'm going to choose that the output is going to be the driver position, which is going to be x1. So if I take my EOMs, I can rewrite the first one in terms of x1 is equal to this stuff, and then I can make substitutions where I put in the appropriate state and derivative of state. And I can do the same thing with x2. X2 dot is going to be this equation, and I can substitute in my q1, q2, q3, q4, and q4 dot. And so now I've got 4 equations, if I count the ones from the previous slide. I've got 4 equations where each state derivative is defined. And so I can fill them in my state matrix and my input matrix. So q1 dot is only equal to q2. And then q2 dot is a little more complicated. q3 dot is only equal to q4. And q4 dot is equal to that. And then I can also fill in my output matrix, where y is equal to only q1. And there we go, we've got it in state space form. And I could go ahead and enter this into MATLAB and run a simulation very easily. Is this better or worse than transfer function form? Well, it's just different. It allows me to see what's going on internally, so that if I wanted, I could have I could look at both the motion of the tire and the motion of the driver. Is it easier? Is it less easy? Well, it depends on how you like to do Laplace transforms. Notice there's no Laplace transforms, it's only derivatives, but I do sometimes have to do a little finessing to get them into first order ODEs, especially if you've got a much more complicated and a coupled system. We'll see some examples of those. But this is state space representation.